everyone. I'm Ruchi Jain, Assistant Professor from ABES Engineering College. Here we will discuss about one-dimensional array address calculation. Outline of this video is as what is array, how we do 1D array address calculation, and example of 1D array address calculation. So here is the topic, what is array? Array is nothing but it is a collection of similar type of data elements within array. Here you can see that there is an array which is named as age, and in this array we have inserted five values as 12, 14, 8, 9, 6, which is considered as age of 5 students. So we can say that array is a data structure which can be defined as finite order set of homogeneous elements. It is finite order. It can't be infinite order. So we move forward. There is an index where formula derivation in one-dimensional array. Firstly, we defined as what is one-dimensional array. One-dimensional array is an array which has a values to be inserted in 1D form. 1D form, like there is one starting point and one end point which is specified by first index value as L, which is called as lower bound of the array, and last value of array is specified by U, which is called as upper bound of the array. So if we have to calculate how many elements are there in a one-dimensional array, if we have given lower bound and upper bound of that array, then the formula for the same is upper bound minus lower bound plus 1. For example, here we have given an example as A. A is an array whose lower bound is 0 and upper bound is 9. So now we have to calculate how many elements are there in this array A by the formula using upper bound minus lower bound plus 1. Upper bound here is 9 and lower bound is 0. Then 9 minus 0 plus 1 equals to 10. So the total number of elements in the array with the size 0 colons 9 equals to 10 elements. Moving further, to find the address of ith index element, we have to take two assumptions. Assumption 1 says as we consider 1 byte storage for each element. We can also consider multiple bytes storage for each elements. Like if we consider integer value, then we have to store 2 bytes of memory, 2 bytes of storage for each cell. If we consider float value, so for float value, there should be 4 bytes of storage for each cell. Second assumption here we considered as array not start from any specific lower bound, but arrays starts from index value 1, so that our formula derivation get easy. So here we consider that base address of that particular array equals to alpha. Now we have to move forward to one step from A1 position to A2 position. Then the address become alpha plus 1. Alpha plus 1 stands for address of A1 plus one step. Move from A1 to A2. Now we have to move from A2 to A3. Then the address become alpha plus 1, which is equals to alpha plus 2. Now we have to move for like A4 position, then the formula become alpha plus 1, which is equals to alpha plus 3. Now we generalize these particular steps, then the address of AI becomes alpha plus I minus 1. This is our equation 1, while we are considering as lower bound of the array as 1, a number of bytes stored in particular cell equals to 1 byte of memory storage. Now we moving forward, we remove our first assumption, which was says that 1 byte storage for each cell. Now we considering that there are n byte of storage for each cell, like I have mentioned before. for integer 2 bytes memory, for float 4 bytes memory, and so on. So we considering n bytes of memory depending on the data type. So then ai equals to alpha plus I minus 1 into n, where n is number of bytes depending on the data type. Now we're removing the second assumption. Second assumption was that first element is at index 1. But in actual scenario, in any data structure, lower bound can be any memory address. But in array, first index value is specified by lower bound. So we considering here the index of arrays starts from lower bound, which is denoted by L. Then ith index element address can be calculated as, to move at the ith position, we have to travel the distance from L to I. That means you have to know about how many elements are there from L to I. So from L, for calculating number of elements from L to I, we consider L as lower bound. And for this particular region, upper bound become I. Then the formula for number of element traversing becomes I minus L plus 1. I is upper bound, L is lower bound. So upper bound minus lower bound plus 1, which is I minus L plus 1. After traversing these number of elements, we move forward to I. That means we reached at I. Then the address of ai become, after replacing I with I minus L plus 1 equals to alpha plus I minus alpha plus I minus L plus 1 minus 1. Plus 1 minus 1 get cancelled from each other. Then the formula become ai equals to alpha plus I minus L into n. That is address of ai equals to base address plus n into I minus lower bound. Moving forward, we discuss one example which specify given a equals to minus 1 colon 10, bytes per cell equals to 4, base address 2000. You have to calculate the address of A7. That means here I equals to 7. N is the number of bytes per cell equals to 4. Minus 1 is lower bound, 10 is upper bound. Then the base address of I formula equals to base address plus n into I minus lower bound. Address of A7 equals to 2000 plus 4 into 7. 7 is I and lower bound was minus 1. So minus minus 1. We calculate this figure, then we get the answer which is equals to 2032, 2032. This is the example where lower bound was negative. Now we consider one example where lower bound is positive value. That means lower bound and upper bound, both values are positive values. So here is this question given a equals to 1 colon 15, where lower bound is 1, upper bound is 15, bytes per cell equals to 3, base address is 1000. You have to find the address of A9. So while finding the address of A9, I is 9, N is 3, lower bound is 1, upper bound is 15. So the base address of, address of AI equals to base address plus N into I minus lower bound gives address of 9 equals to 1000 plus 3 into 9 minus 1. By calculating this equation, we get the answer 1024, which is the address of A9. Thank you.